Okay, so hello everyone. Welcome to my MSR thesis talk and PhD speaking qualifier. I am Tarasha, and today I'll be talking about my work detecting invisible people, which was recently accepted at ICCV 2021. And as you can see as the end task, we are interested in the localization of fully occluded people in videos. So I'll be first discussing the motivation for the task we introduce, the challenges we face in defining this new task, some past work that is closely related to us, the method we propose, and the experimental results, followed by some discussion of future research directions. So to start with, consider this real world scenario where a person moves along the sidewalk, gets completely occluded behind this yellow taxi and then the pickup truck, and then suddenly reappears at the intersection. Now, in such a scenario, for safe operation, we would want to prevent the autonomous agent from crashing into this person. And this can only be achieved if the agent knows how to act appropriately during the occlusion phase. So existing vision algorithms don't have this online skill, and they instead wait for the object to reappear, and then they go back in time to reason about the occluded time steps. However, for humans, there exists considerable psychological evidence that this online reasoning of occluded objects develops as early as in young infants. Now, even though this is such a basic skill in humans, our vision algorithms do not possess this capability. And in fact, this task is not really the focus of any of the detection, tracking, or forecasting benchmarks. So here I'm showing annotation examples from YTVIS, TAO, and TLP, which are multi-object tracking datasets. And you'll see that all of these datasets label only the visible extent of objects when they are partially occluded, and then they don't label them at all when they are fully occluded. And only a few datasets exist that implicitly serve as data for this task. But then in these datasets also, more than 85% of the objects are always visible. So clearly the online detection of occluded objects has not really been the focus of the datasets and by extension of the metrics, simply because these objects are so low in number that the metrics naturally de-emphasize performance on them. Now, if you really think about it, the mere definition of this task raises a number of fundamental questions. For example, how does one even annotate fully occluded objects so as to obtain ground truth data for this task? And what do we really expect algorithms to output? Should it be a mask, or more coarsely, should it be a bounding box? Or even more coarsely, should it just be a distribution of bounding boxes in space? And how strictly should we be evaluating these outputs? So to answer these questions, we conduct a human vision experiment where we ask 10 people to label approximately 10 tracks each. And in each of these tracks, the person of interest gets occluded for at least 10 continuous frames. And the job of the annotators is to create a bounding box wherever they think the person could be without having access to any of the future frames. So now here I am showing one such track for the person in the red t-shirt, annotated by 5 people. And you'll see that whenever this person is visible, the annotations overlap each other by a lot. But then when this person becomes invisible, the boxes kind of disperse a bit, but they're still fairly agreeing with each other by a large amount. And this shows that humans are able to use past temporal context to localize occluded people. So here I'm visualizing one particular frame from the occlusion phase. And you'll see that all the human, online human annotations approximately result in a distribution. For this online task, we expect our methods to at least output a distribution of boxes instead of reporting a single bounding box. And then next, our quantitative results of the human vision experiment suggests the following, that for people with less than 10% visibility, whom we call fully occluded people, there is a 60% IOU agreement between annotators in the localization of occluded people. Now, this is a big number suggesting that the task is not impossible, but then it is also not as easy as detecting visible people, for which our annotators show about an 80% IOU agreement. And quite unsurprisingly, this is also what we observe with the state-of-the-art detectors and trackers. So when they are evaluated only on occluded people, their performance reduces to a mere 28% from 68%. So given the difficult nature of the task, we can make our metrics more lenient by lowering the thresholds used in evaluation, for example, while computing IOU. And finally, here I'm visualizing a single track with online annotation as well as offline annotation. And you'll see that there's a considerable difference between the two at some time steps. And we note that offline annotation is a more reliable annotation strategy because one has access to more information because you can access the future frames. So these are all the answers we get from our human vision experiment, which we use in this work. And now, given this is a fairly developed skill in humans and one that is safety critical in scenarios such as autonomous driving, we can now think about what a method should look like for detecting occluded people. So first of all, one fact is that this problem is set in videos and it is temporal in nature. So our method should kind of have the same flavor as tracking algorithms based on, for example, Kalman filters, because temporal processing like tracking would be an intermediate task for us. So it is useful to quickly go over what a standard tracking by detection pipeline using a Kalman filter would look like. So at every frame of a video, we have in memory a set of active tracks. And each of these tracks has a velocity estimate associated with it, which you have aggregated from all the previous time steps. So using this velocity estimate, we want to forecast all the active tracks one time step into the future. And then at that future time step, there also exists a set of detections. And what you basically want to do is match your forecasts to the observations that you get at the future time step. So in case a match is found, you will refine the estimates of your active track, for example, the velocity estimates. And if there exists a new person for which a track does not already exist, we will start a new track for it. And then if you expect a detection to be at some place in the XY coordinate in the image, but you don't find it, you will take some decision to terminate the track of that person. So now this last step of track termination is the most crucial for detecting occluded people. And we basically want to answer this crucial question that in case of no visual observation, should we kill the object's track if it is not visible to us? Or do we keep forecasting because this could be an occluded person? So the main proposed hypothesis of our work is that one should use depth to answer this question and decide whether a person is occluded or not. Now for in the wild videos, especially with moving objects and with unknown calibration, this depth is hard to get by traditional multi-view methods, but we find that learning-based monocular depth estimators, they are advanced enough to give us the rich relative depth information. And Using these, the decision of what to do with the forecasted box, in case it is occluded or not, that decision can be taken easily. So before we see how, let us look at some prior work in this direction. So a number of methods do track in 3D by directly detecting objects from point clouds and then linking them. And because of this, they are heavily dependent on sensors like LiDARs or calibrated stereo setups. But in contrast, we assume access to only a depth map, which does not give us metric depth or any calibration information. Now, sometimes in the case of stationary camera videos, it is possible to reason in 3D by estimating a ground plane, either by using a homography or by using multi-view setups. But for moving camera sequences, estimating the ground plane is non-trivial. And we especially consider the monocular case where the camera can move. And some approaches use some form of occlusion reasoning to improve 3D tracking, but then the occlusion reasoning itself is not the focus of these works, which is in contrast to us, where we only, in addition to evaluating the standard overall metrics, we also evaluate the occlusion reasoning of our approach. So 2D or 3D tracking, they are solved either in the offline or the online, in both the cases. And in the offline case, re-identification is incorporated into tracking using post hoc linking of tracks, such as by graph-based optimization. But for our task, once again, we have to reason about occluded objects online, as we cannot wait to see them again at some future time step. And then in the online case, some approaches that are based on Kalman tracking, like sort or deep sort, they do maintain online internal forecasts of tracks, but these are not reported in the output simply because they are so error prone. And we'll see shortly how methods like deep sort can be modified in a straightforward way to reduce these errors, but still we'll see that the maximum gain in performance will only come when we use depth. And finally, similar to tracking, our work is also closely related to trajectory forecasting. So most of these forecasting algorithms, they try to learn complex social cues and semantic information of the scene. But we show that this is unnecessary for short range occlusions, which can be much better modeled by simple linear dynamics. So given the past work in this direction, let us look at a straightforward way to modify an existing state-of-the-art algorithm like deep sort to detect occluded people. So we could first start by reporting all n number of internally generated forecasts in deep sort, which it otherwise does not report. And we can tune this, we can tune this n parameter to reduce the number of false positives that these forecasts would generate. So this actually proves to be a naive but reasonable baseline strategy for detecting occluded people. But still in this visual, you'll see that some tracks of people, they just fly off in different directions. And sometimes, for example, some boxes lie on the road or in the sky. But we know from looking at these frames that nothing actually lies there, and that particular region in the image on the road or in the sky is empty. So we should definitely be able to do better than this. So a lot of these forecasts can be made more intelligent or less error prone by using depth. And that is where our key hypothesis lies. And I'll now explain how we can incorporate depth to do this in the context of a Kalman tracking algorithm like deep sort. So technically speaking, the real question we have to answer for every person track is that in case of no visual observation, do we kill the track or do we keep forecasting it and retain it? Because this could potentially be an occluded person. So In order to appropriately deal with such a scenario, we propose to linearly forecast in the XY image coordinate, like most prior work, and a relative Z coordinate, which we get from every frame's depth map. So here on the left, I'm showing a person's detection on the image plane, which I have kind of lifted into 3D on the right. So the main advantage of forecasting in 3D in such a way is that at some future time step, if this person becomes occluded, we will be able to get the true depth of the occluded person. And it is not possible to recover this true depth otherwise, because conventionally the camera and hence the depth estimator, they see only the visible objects in the scene. So if you were to query the true depth of this black coat person who is occluded, you would actually get the depth of the lady in green, which would be the apparent depth. So now, how do we get the relative Z for every person? So we simply average the depth of people across their masks or bounding boxes to get one number for every person in the scene. And this is approximately the type of Z coordinates that our method gets to see. Now, once we have this relative depth ordering and we know how to forecast in the XY image coordinates and a relative Z, we need some mechanism to decide the validity of forecasted boxes that don't have a corresponding visual observation. So here there can be two cases. Either the forecasted box can be correct, or it can be incorrect and not belong to an occluded person. So when will this forecast be correct? When its Z coordinate will lie beyond the free space horizon that I show on the right. So this free space horizon is like a surface or just a set of points where the rays from the camera would hit the visible surface. And in other words, this free space horizon is the depth map that you get from the depth estimators. So the region beyond the free space horizon is unknown, and this is the region where occluded people can lie. And everything in front of the horizon is free space. And we know that nothing exists there because the depth map gives us that information. So this was the first case where if and only if a forecast lies in the unknown region, it is correct. And if instead the forecast lies in the free space, it would be incorrect. So for example, for this particular forecast of the person that lies in a free space between the camera and the storefront, we should have some recovery mechanism that handles this incorrect forecast. So in our algorithm, we introduce some tunable parameters that decide whether to suppress the track or delete the track based on how much it is violating the free space constraints of the scene. Now, since we are operating in this projective space of XY image coordinates and a relative Z, we also have to account for changes in pedestrian motion in space. So naturally, people that are closer to the camera, they suffer a lot of change in their aspect ratio as they move their hands or legs. And then their image translation is also large for small time steps. But on the other hand, because of the parallax effect and the projective geometry of the scene, this is not the case for people far away. So you can see here that as people walk further away from the camera, their bounding box does not change that much. And the box translation as projected onto the image plane is also very small. So in a sense, our algorithm should enforce smoother tracks for objects far away. And how we implement this in our algorithm is by scaling the process noise in the Kalman filter by inverse depth. So basically, objects far away have less noise in their forecasts, and objects close by will have greater. And we arrive at this result with a simple derivation based on projective geometry. And for all the other details related to this result, I would refer you to the main paper. Now, finally, specifically for moving camera sequences, our forecast at every time step should also account for the translation due to the camera ego motion. So for all the moving camera sequences, we follow prior work and we estimate the frame to frame ego motion by a homography warp. So on the left here, you'll see once again, you'll see the forecasts flying off in space. And this happens in the absence of ego motion compensation. But on the right, all of these forecasts are kind of taken care of by aligning them with the homography warp. Okay, so all these three components are the major parts of our pipeline, and specifically our main contribution lies in proposing the concepts of free space filtering and depth-aware noise. And all this depth-based reasoning is baked into our Kalman filter formulation and the data association steps. So I've tried to keep the method description abstract, and I've skipped over most of the technical details, but all of these can be found in the pseudocode of our algorithm in the paper draft. So the pseudocode explains how we implement free space filtering, which is the retention, suppression, or deletion of tracks based on the free space constraints of the scene. And then how we implement the depth-aware noise, which takes care of pedestrian motion in the projective space, and also the ego motion compensation part of our pipeline. Okay, so that brings us to experimental setup and results. So to test this approach, we use existing tracking benchmarks, namely MOD 17, MOD 20, and PANDA. And we repurpose them in the sense that we divide the annotations in these data sets between visible and invisible people using a visibility field label. And according to the labeling style in each of these data sets, we call occluded people as being less than 10% visible for MOD 17 and the MOD 20 data sets, and as being less than 33% visible for the PANDA data set. And this definition of occluded people is actually useful in defining the metrics, which I will describe next. Now, with the human vision experiment at the start of the talk, I tried to motivate how all methods should report distributions of occluded people. And in order to evaluate this distribution, we introduce a probabilistic metric, which is a modification of the standard F1 score metric. So here on the left, I'm showing the input RGB video, and on the right, I show a top-down view of the same scene. So here the y-axis is the relative depth of the scene, and the x-axis is the image x coordinate. And the top-down view shows a truncated Gaussian distribution of where the person could be, and the truncation actually reflects the free space horizon at that height of the bounding box. So basically what this means is that when a person is occluded, the uncertainty in its location should approximately take the shape of its occluder. So for longer time steps, you'll see that as the person remains occluded, this uncertainty in position grows and it increases with time. So given this distribution, we sample k possible positions from this distribution at every time step for every person. And what this means is that when we match this distribution to the ground truth to find the true positives or the false positives, etc., we consider the sample that has the highest IOU with a given ground truth. So this gives us a top KF1 metric for occluded people. And this is the main metric we use to evaluate the detection performance for fully occluded people. Okay, so before going to numbers, I'll start with some qualitative results. So this is one of the most basic results where I show a person in green being detected through two complete occlusion phases. And simultaneously, its true depth is also recovered in the top-down view. Okay, here is another example where two people are crossing each other and they are pretty close to each other, even in terms of their depths. And we are still able to successfully detect the person in green and then simultaneously recover its true depth in the top-down view of the scene. So on the last slide, I showed an example of a person-person occlusion, where both the occluded person and the occluder were being tracked. But here I show an example where the occlusion occurs due to the natural scene elements, for example, a car in this case. And we are able to model these person-object occlusions also because we determine the validity of forecasted boxes by checking the depth map of the entire scene. And we are not dependent on only the tracked objects and their relative z coordinates to detect these occlusions. Okay, so here on the left and the right, I'm showing top-down views of the same scene for the same time steps. And on the left, I plot the z values of all visible and occluded people as seen from the single frame depth estimates. And on the right, I'm comparing this with the depth estimates for occluded people and visible people as returned by our pipeline. So on the left, you'll see that the tracks jump a lot as the occluder passes by a person that eventually gets occluded. But on the right, this is not the case because now we are able to recover the true depths of occluded people. So the tracks don't jump in the z coordinate any longer. Okay, so moving on to some quantitative analysis, I am first showing the most important result of all, which is comparison with the state of the art on the mod 17 and the mod 20 test sets. So I report two metrics here just to keep everything simple. First is our probabilistic metric, which is the top k f1 with k equal to 5. And then the second is a standard tracking metric, which is IDF1. And higher is better for both of them. So for mod 17, we improve by 5% over the state of the art for the top 5 F1 metric and by 4.3% for the IDF1 metric. And similarly for mod 20, we improve by 2.7% and 1% for the top 5 F1 and IDF1 metrics respectively. So at the time of submission to ICCV, we ranked first on the occluded metrics leaderboard for both the data sets, mod 17 and 20. Okay, so these were the results on the test set, but we also ablate with 8 different detectors and trackers on the train sets of all the 3 data sets. And here I'm only reporting the average improvement in performance across these 3 data sets. So for MOT 17, this mean gain in performance is 9% for top 5 F1 and 8.6% for IDF1. For mod 20, this is 3.6% and 2.1%. And for Panda, this is 4% and 2.1%. So Note that we tune our parameters on the mod 17 train set for the faster RCNN set of detections, and we use these parameters only across all other detectors, trackers, and across all the data sets we use. So basically, we can do this because our approach can be used as a plug and play module on top of any detector or tracker. So we'll now see how each component of our pipeline helps in the detection of occluded people. So we'll take deep sort as the baseline algorithm, and I'll discuss the progressive effect of adding every component of our pipeline. So first, if we just output every internally maintained forecast in deep sort, which are otherwise not reported by deep sort, we see a 1.4% gain in top 5 F1. And mostly this occurs because of the increase in recall. But this particular step also hurts our precision by a lot, and the precision drops by 40%, which is basically recovered by all the other components of our pipeline. So when we add ego motion compensation to this, the top 5 F1 again increases by 2.4%. And most of this increase in performance is due to the increase in precision, because now we are reducing the number of false positives. And then if we add free space filtering to this, the top 5 F1 again increases by 3.5 points. You'll see that most of this gain is because of the reduction in the number of false positives. So the precision jumps up by 14.6%, but then the filtering also sometimes reduces our true positives, because of which the recall decreases. Okay, so the last component is the depth aware noise, and that also increases our top 5 F1 by 4%. And most of this gain in performance is because of the increase in both the precision and the recall.
Sorry, quick clarification. Here the deltas are all with respect to the previous row, not the first row, right?
Yeah. So this is, these are not cumulative. These are.
Good.
Okay, so I'll show a couple of failure cases now. So in this one, the lady highlighted in green, while she is visible, her projected translation on the image plane is towards the left. But then as soon as her occlusion phase starts, she starts moving towards the right. And then because we assume linear dynamics, our forecast still keeps moving towards the left. And this is another failure case where the person in green moves behind a wall. But then because no ground truth exists for this person, even when we detect it correctly, we are penalized for it. And our detections are counted as false positives. Okay, so that was all about the task and the metrics and our method and the results. So in summary, I want to highlight the two most important takeaways from this work. So first is that monocular depth estimation has reached a stage where it is now usable for downstream tasks. And it might only give us relative depth without 100% per pixel accuracy, but some representations of this depth, for example, relative depth orderings, as we showed in our work, they are definitely usable for downstream tasks. And then second, as a community, we have to focus on developing the skill of object permanence in our algorithms. And this is a pretty easy job for infants, yet no data sets exist that would look at detection, tracking, or forecasting in this way. And for autonomy and safety critical scenarios, and even in general, we have to start looking at this problem. And on a lighter note, here is a video of me trying out the detecting invisible people experiment on my nephew. And this is me here at the back. And even though I could not explain to him what he really had to do, he just involuntarily still tracks me, and he goes where he expects me to go while being occluded behind the staircase. Okay, so I see that Ayush has a question.
Oh, I just raised the hand because it was the end of the talk after the.
Okay, cool.
Sorry.
No problem. Okay. So let me just quickly tie some future directions with this work. So what are the two main things that this task, or specifically our pipeline, needs? One is good A-modal detectors for tracking, and the other is good depth estimators. And I'll now discuss the issue with each of these now. So first, it is impossible to detect completely occluded people without having good A-modal detectors, or detectors that would label objects to their full extent, even when they are partially visible. But these detectors don't exist because there does not exist a data set which would have a rich distribution of scenes or objects with A-modal bounding box annotations. So in this regard, we are in the process of building a data set called tau A-modal, which extends all tracks in tau with A-modal bounding boxes, even for completely occluded objects and not just people. So our hope is that this will be the most diverse real-world benchmark for A-modal detection and tracking, and for the localization of occluded people. So tau A-modal will have annotations at 1 FPS for both in-frame and out-of-frame occlusions, as I show here in the video. And we are currently running a pilot on all the 7 subsets in tau. And there are 2 rounds of quality control on the pilot annotations. Until now, about 30,000 boxes have been labeled A-modally. So 87% of these have actually been modified from tau, which would mean that these correspond to partial occlusions. And then 7%, 2,000 of these boxes, they are new, which would mean that they correspond to fully occluded objects. So out of these 2,000 boxes, 93% of these boxes are certain, which means that our annotators are confident of their labeling, so which is a great number. So second, for depth estimators, there is this harmful protocol which forces us to resize the images to a smaller input resolution during inference. For example, for MIDAS, by default, all the input has to be resized to 384 by 384. Now, inference at such a low resolution takes away a lot of detail in the image. So here I'm showing an input image from, or input video from one of the data sets we evaluated on. And you can see that by default, at the default input resolution, all the people are lost in the output because they are almost like a high frequency detail in the image. And if I increase the input resolution by 4 times, I start recovering some detail in the videos. And like in this case, you'll see some people start appearing in the depth map. But then as we increase the input resolution by a lot, in the hope to recover more high frequency detail, we see that this harms the overall geometry of the scene. And we start getting this patchy output. So we did explore a few ways to post-process these outputs, and I did a bunch of analysis on what the inductive biases of these networks would be. But I think for this particular direction, we should be thinking more broadly about how to correctly design depth estimators that are, for example, independent of input resolution. And this may involve thinking about how to send in the information about camera intrinsics, or might involve thinking about some architectural shifts, like instead of looking at images as a set of pixels, maybe you should look at images with a more implicit representation, and maybe you should look at them as sets of rays generating from a camera center. So this is one of the directions that I would like to explore in the future. Okay, that was all from my side. And lastly, I want to acknowledge all the efforts of Deva and especially Achal in advising me throughout my master's, and for giving me important feedback that was sometimes hard to hear. And all my lab mates, especially Kengshan and Piyun, and all the internal reviewers that reviewed our paper. And also my family, who always keeps me high-spirited. Cool.
Okay, maybe we'll give a virtual clap. Great job, Trasha. Maybe we'll just go ahead and swing into, right on time too. We'll swing into questions. So we'll start with the committee.